Welcome students in online class for a channel of Easy and Simple Physics by Joshi Sir Partur for the student of 11th and 12th Science. Today we learn about a question bank provided by State Board. For the chapter number 12, Electromagnetic Induction, for the subject Physics. Question is multiple choice type question. Each question carries 1 mark. So the first question is, in which of the following device the eddy current is not uses? Option will be electromagnet, induction furnace, electric heater, magnetic braking trains. Here the answer will be electric heater, because by electric heater it converts electrical energy into heat energy. Electric heater is safe than gas. Electric heater will help to save the energy cost. This device supplies heat, for example, for a radiator or converter. This heater is heats only by water. Question number 2. Ideal transformer has 100 turns in primary and 250 turns in secondary. The peak value of AC is 28 volt. The RMS secondary voltage is nearest to. Option is first option 100 volt, B option 70 volt, C option 50 volt, and D option 40 volt. So answer is 50 volt, because a given data will be primary number of turns is 100, secondary number of turns is 250, EMF across primary is 28 and EMF across secondary can be calculated. So first we know that for ideal transformer IP EP equal to IS ES. Here EP is directly proportional to NP, and so that EP upon ES is equal to NP upon NS. So E0, that is peak value across secondary, is equal to peak value E0P multiplied by NS upon NP. If we take 28 multiplied by 250 upon 100 is equal to E0S, it will be near about 70. But we can find ERMS. So ERMS equal to peak value of EMF upon square root of 2. E0 upon square root of 2, that will be 70 upon square root of 2, which is 70 upon 1.414, which is near about 50 volt. Third question is, role of inductance is equivalent to. First option A is inertia, option B is force, option C is energy, and option D is momentum. Here answer will be option A, that is inertia, because as an inductor shows down changes in current in the circuit, thus it provides an electrical inertia and acts as a ballast. So in non-inductive coil, L approximately equal to 0. So here electrical energy is converted into heat energy due to ohmic resistance of coil. So inductive coil or inductor stores part of energy in the magnetic field of coil. Therefore, when current through inductor is increases, but this energy is released when current in inductor is decreases. Question 4. It is the energy stored in a 50 millihenry inductor carrying a current of 4 ampere is option A 0.4 joule, option B 0.1 joule, option C 0.4 joule and option D 0.01 joule. Here answer is option A 0.4 joule, because given data will be, we can find out energy EM equal to question mark. Here inductance L is given as 50 into 10 raised to minus 3 Henry and current I is 4 ampere. So we can use EM is equal to half Li square. If we substitute the values here, half multiplied by 50 multiplied by 10 raised to minus 3 into 4 square. So 50 divided by 2, that is 25 into 10 raised to minus 3 into 4 square. So 25 into 10 raised to minus 3 into 16, that is 400 into 10 raised to minus 3 joule. So here answer will be 0.4 joule. In the expression E equal to minus d phi upon dt, the negative sign signifies that option A, the induced EMF is produced only when magnetic flux decreases. Option B, induced EMF is opposite to the change in magnetic flux. Option C, the induced EMF is opposite to the direction of flux. And option D, the induced EMF is independent of change in magnetic flux. So here answer will be option B. The induced EMF is opposite to the change in magnetic flux, because according to Lenz's law, it gives the direction of induced EMF which opposes the change in magnetic flux. Question 6. The two pure inductors, each of self-inductance is L, are connected in series. The net inductance is option A L, option B 2L, option C L upon 2 and option D L upon 4. So here answer is option B 2L, because for series combination the two inductor each having same inductance is L net is equal to L1 plus L2, that is equal to L plus L, which addition becomes 2L. So net inductance will be 2L. Question number 7. A magnet is moved towards a coil. Number 1 quickly, number 2 slowly. Then induced EMF is option A larger in case of 1, option B smaller in case of 2, option C equal in both case 1 and 2, and option D larger or smaller depending on radius of coil. So here answer will be option A, that is larger in case 1, because when magnet is moved towards the coil quickly, then the rate of change in magnetic flux is larger. But if magnet is moved towards a coil slowly, then large EMF is induced due to quick movement of the coil. So answer will be option A, larger in case 1, that is quickly. So question number 2, it will be very short answer type, means VSA type of question. Each question carries 1 mark. So in that question, so first question will be state the Faraday's law of electromagnetic induction. Answer will be Faraday's law of electromagnetic induction state that whenever there is change in magnetic flux associated with coil, an EMF is induced in the coil. Number 2, the magnitude of EMF induced in the coil is directly proportional to the rate of change in magnetic flux associated with coil. Question number 4. State the condition at which we say the two coils kept close each other are perfectly coupled each other. Answer will be when the coefficient of coupling, that is K, is 1. Then we say that two coils kept close each other are said to be perfectly coupled with each other. State the mathematical relation between number of turns in primary coil to the secondary coil in step-up transformer. Let NP is number of turn in primary coil, NS is number of turn in secondary coil, EP is EMF across primary, ES is EMF across secondary. We know the relation between EMF and number of turn, that is EMF is directly proportional to number of turn. So EP is directly proportional to NP and ES is directly proportional to NS. Therefore, EP upon ES is equal to NP upon NS. So we say that in this case, when EP is greater, NP is also greater. But in step-up transformer, NS upon NP is equal to ES upon EP. So here NS secondary, number of turns in secondary is greater than number of turn in primary. State the Lenz's law. The Lenz's law states that the direction of the induced current in such as to oppose the change that produces it. The change that induces a current may be number 1, the motion of conductor in a magnetic field. Number 2, the change in magnetic flux through a stationary circuit. Question number 5. A pair of adjacent coil has a mutual inductance of 1.5 Henry. If the current in one coil varies from 0 to 20 ampere in 0.5 second, what is the change in flux linked with the other coil? Here data is given as mutual inductance capital M is equal to 1.5 Henry. Initial current 0. Final current I2 equal to 20 ampere. In time dt 0.5 second, and we can find change in magnetic flux. We know magnetic flux is directly proportional to I. So phi equal to Mi. Phi 21 is equal to Mi2 and phi 12 is equal to Mi1. Therefore change in magnetic flux phi 21 minus phi 12 d phi is equal to M in bracket I2 minus I1. So 1.5 in bracket 20 minus 0, that gives 1.5 into 20 it gives us 30 Weber. So answer will be 30. An aircraft of wing span of 50 meter flies horizontally in earth magnetic field of 6 into 10 raised to minus 5 Tesla at a speed of 400 meter per second. Calculate the EMF generated between the tips of the wings of aircraft. See here, numerical can be solved like given data. Length is 50 meter. Magnetic induction vector B is 6 into 10 raised to minus 5 Tesla. Velocity is 400 meter per second, and we can find out EMF. So EMF generated between tips of the wing of aircraft is E equal to vector B LV, which is equal to 6 into 10 raised to minus 5 into 50 into 400. That gives us 3 into 4, that is 12 into 10 raised to 4 into 10 raised to minus 5. So here EMF is 1.2 volt. Answer will be 1.2 volt. Another question, question number 7. A coil of self-inductance 3H, 3 Henry carries a steady current of 2 ampere. What is the energy stored in magnetic field at the coil? So given data will be L equal to 3 Henry, I equal to 2A, and energy equal to question mark. So energy stored in magnetic field formula will be vector E equal to half Li square. Substitute the values, half into 3 into 2 square, 2 get cancel, 3 into 2 get 6 joule. So energy stored in magnetic field will be 6 joule. Another question will be short answer 1, essay 1 type questions. Each question carries 2 marks. So in that section we can solve the first question, that is why and where are eddies current are undesirable and how they can be minimized. So here we can write answer. Eddy current can produces heat energies. When a thin metal plate is moved towards magnetic field, but this eddy current is undesirable because due to eddy current heat energy produces, so metal get or is vaporized, and which damages the plate. But by keeping number of thin metal plates which are packed to form a bundle or packet called core, so which prevents the heat energy. To avoid undesirable effect of eddy current, core must be used. So this will be the answer for the given question. So question 2 will be define self-inductance and mutual inductance. Answer is self-inductance is also said to be coefficient of self-inductance of a coil. Is defined as the EMF induced in coil per unit time or the rate of change of current in same coil, or the ratio of magnetic flux linked with the coil to the current. It is called self-inductance. Let phi is directly proportional to I. Therefore, phi equal to Li, where L is called as coefficient of self-inductance. So we know E equal to d phi upon dt, which is equal to d upon dt Li. So therefore E equal to L di upon dt, that is self-inductance. So L equal to E upon di upon dt. Second definition is mutual inductance. Mutual inductance is also said to be coefficient of mutual inductance of two magnetically linked coils is equal to the flux linkage of one coil per unit current in the neighboring coil or primary, or the EMF induced in one coil, that is secondary coil, per unit time rate of change of current in the neighboring coil, that is primary. We know phi directly proportional to I, therefore phi equal to Mi. We know E equal to d phi upon dt, therefore d upon dt in bracket Mi. So E equal to m di upon dt, and therefore m equal to E upon di upon dt. Question number 3. Explain why the inductance of two coils connected in parallel is less than the inductance of either coil. Answer will be when two coils are connected in parallel. Assume that mutual inductance can be ignored. Let self-inductance of first coil is L1 and self-inductance of second coil is L2. So here, when two coils are connected in parallel, then equivalent inductance is 1 upon L parallel equal to 1 upon L1 plus L2. Therefore, 1 upon L parallel equal to L2 plus L1 upon L1 L2, and therefore L parallel equal to L1 L2 upon L1 plus L2, which is less. So L parallel is less than L1 and L parallel is also less than L2. Means in parallel combination, equivalent inductance is less as compared to each inductance of coil. Question number 4. An EMF of 96 millivolt is induced in the winding of a coil when current in a nearly coil is increasing at the rate of 1.20 ampere per second. What is the mutual inductance of two coils? Here, given data, it will be E equal to 96 millivolt, that is 96 into 10 raised to minus 3 volt. Di upon dt is 1.20 ampere per second, and m can be calculated. So we know E equal to m di upon dt. So m is equal to E upon di upon dt. So capital M is equal to 96 into 10 raised to minus 3 upon 1.2. So that here 8 into 10 raised to minus 2 Henry, and so here 80 into 10 raised to minus 3 Henry, and therefore mutual inductance it will be 80 millihenry. That will be the answer. Question number 5. Calculate induced EMF between the end of an axle of a railway carriage, which is 1.75 meter long, traveling on a level ground with uniform velocity 50 km per hour. The vertical component of earth magnetic field, that is BV, is 5 into 10 raised to minus 5 Tesla. So here we can write a data. Given data for answer will be L, length is 1.75 meter. Velocity will be 50 km per hour. So we can calculate 50 into 1000, that is meter, upon 60 multiplied by 60 means meter per second. So what happened? 0 get cancel, 500 upon 36 meter per second. And here BV, that will be 10 raised to minus 5 Tesla. So we can calculate E, the value of E. Here E equal to BV into LV. Substitute the value BV, that is 5 into 10 raised to minus 5 into 1.75 into 500 upon 16. If we can calculate here 5 into 1.75 into 125 upon 9 into 10 raised to minus 5. Here we can write as 625 into 10 raised to minus 5 into 1.75 upon 9. By calculating it, taking log and antilog, here EMF which is induced in the end of axle of railway carriage will be 1.214 into 10 raised to 2 into 10 raised to minus 5. That is 1.214 into 10 raised to minus 3 volt. So EMF which will be induced will be 1.214 millivolt. That is the answer for the given numerical. So here question number 6, that is the magnetic flux through a loop varies according to the relation phi equal to 8 t square plus 60 plus 2, where phi is in milliweber and t is in second. What is the magnitude of induced EMF in the loop at t equal to 2 seconds? So here we can write a data. That data will be phi equal to 8 t square plus 60 plus 2. So here we can calculate EMF. Time is given, that is dt equal to 2 seconds. So we can write as, according to Faraday's second law, E equal to d phi upon dt, E equal to d upon dt in bracket 8t square plus 6t plus 2. So here we can write 8 dt square upon dt plus d upon dt into 60 plus d2 upon dt. Here d2 upon dt get cancel. Derivative of dt square, that is 16t plus 6 milliweber. So we can write as for t in second. So here for t it will be given as 2 seconds. 16 into 2, that is 32 plus 6 into 10 raised to minus 3 Weber. So we can write as 38 into 10 raised to minus 8 volt. So EMF which is induced in the loop at 2 seconds will be 38 millivolt. Question number 7. Difference or distinguish between step up and step down transformer. So here one column it will be written as step up transformer, another will be written as step down transformer. The first point is, in step up transformer output voltage is more than input voltage, whereas in step down transformer output voltage is less than input voltage. Number 2, number of turns in secondary coil is more than number of turns in primary coil, whereas in step down transformer number of turns in primary is more than number of turns in secondary. The third will be output current is less than input current, whereas in step down transformer output current is more than input current. And fourth will be primary coil number of turns of copper wire is less, which is thick, whereas in step down transformer primary coil In primary coil, number of turns of copper wire is more, which is thin. These are the differences between step up and step down transformer. Another section can be seen, that is short answer 2. Essay 2 type of question. Each question carries 3 marks. So the first question in this section will be, what is transformer? Explain step up and step down transformer. So here, first of all, we have seen a transformer is an electrical device which uses mutual inductance to transform electrical power at one alternating voltage into electrical power at another alternating voltage. First of all, we have seen step up transformer. A transformer which increases the amplitude of alternating EMF, that is change a low voltage of alternating EMF with lower current, called step up transformer. In step up transformer, less number of thick copper wires are wound on one arm of core. Across primary, input voltage is applied. Across secondary, step up transformer, large number of copper wires are wound in another arm of core. A core is a thin rectangular frame which help to reduce the eddy's current. Let we see that NP is number of turn across primary of transformer. NS is number of turn across secondary of transformer. Next, IP is current in primary of transformer. Next, IS is current in secondary of transformer. Let EP is EMF across primary, and let ES is EMF across secondary of transformer. For step up transformer, NS is greater than NP. So NS upon NP is greater than 1. Means EMF across secondary is greater than EMF across primary. So current IP is greater than IS. Therefore, ES upon EP equal to IP upon IS equal to NP upon NS. So here, this is the relation for step up transformer. But here we can see that step down transformer, a transformer which decreases the amplitude of alternating EMF in the change of high alternating EMF into low voltage alternating EMF with high current is called step down transformer. In step down transformer, small number of thick copper wires wound on one arm of the core, said to be primary. Across primary, input voltage is applied across primary of transformer. Across secondary of step down transformer, small number of thick copper wires are wound on one arm of the core. Across secondary, output voltage is obtained which is low at high voltage. Therefore, for step down transformer, secondary number of turn means NS is less than NP. Here ES is less than EP. Here IP is greater than IS. Therefore, NS upon NP is less than 1. So, ES upon EP equal to NS upon NP, which is equal to IP upon IS. So, here NS upon NP called as turn ratio. Figure is given. So here question number 5, that is determine the motional EMF. Question number 2, that is determine motional EMF induced in a straight conductor moving in a uniform magnetic field with constant velocity on the basis of Lorentz force. Lorentz force is, so answer is an EMF induced in a conductor as circuit by moving in a magnetic field with constant velocity called motional EMF. First of all, we can consider a straight rod or conductor of length L, which is placed in a uniform magnetic field perpendicular to its plane of uniform magnetic field of induction vector B, as shown in figure. Suppose external agent moves to the right with constant speed vector V perpendicular to magnetic field of induction vector B. The free electrons in the conductor or rod experiences a Lorentz force. So F is equal to Q into vector V cross vector B. Here, using right hand rule or for cross product, the Lorentz force on negatively charged electron is downward. So Lorentz force vector F move the free electrons in the wire from P to Q so that P becomes positive with respect to Q. Thus there is separation of charges to the two ends of the wire until an electric field builds up to oppose further motion of charges. In moving the electron a distance L along the wire, work is done by the Lorentz force. So W equal to FL, which is equal to Q V B sin theta into L, which is QVBL, because as theta equal to 90 degree, sin 90 degree equal to 1, which is the angle between them. Since electric work done per unit charge is EMF which is induced in the wire. So E equal to work done upon charge. So W upon Q, which is equal to QVBL upon Q. Q get cancel. Therefore E equal to BLV. In electric field, vector V cross vector B equal to F upon L. Therefore, in potential difference PD or EMF induced in the wire PQ, EMF E equal to BLV. Primary of transformer. Question number 3. Primary of transformer has 40 turns and works on 100 volt and 100 watt. Find the number of turns in secondary to step up voltage to 400 volt. Also calculate current in secondary and primary. So given data, number of turn in primary 40, EMF in primary 100 volt, power 100 watt. Number of turn in secondary can be calculated. EMF in secondary 400 volt. Current in secondary can be calculated and current in primary also can be calculated. So for step up transformer, ES upon EP equal to NS upon NP. So NS equal to NP multiplied by ES upon EP. So 400 divided by 100 into 40. So 0 get cancelled. So number of turns across secondary equal to 160. For ideal transformer, IP EP equal to IS ES, which is power, which is given as 100 watt. So IS equal to power upon ES. So here 100 upon 400. So it gives us 1 upon 4. That will be current across secondary is 0.25 ampere. But IP EP equal to 100 watt. So IP equal to 100 watt upon EP. 100 upon 100 get cancelled. So current across primary is 1 ampere. So therefore number of turn across secondary is 160. Current across secondary is 0.25 ampere and current across primary is 1 ampere. That is the answer. Question number 4. The primary and secondary of coil of a transformer each have an inductance of 210 raised to into 10 raised to minus 6 Henry. The mutual inductance capital M between winding is 4 into 10 raised to minus 6 Henry. What percentage of flux from one coil reaches the another coil? Question mark. Here two coils are given having same inductance. So L primary across L secondary is equal to 200 into 10 raised to minus 6 Henry. Mutual inductance is given, that is 4 into 10 raised to minus 6 Henry. So first of all we can calculate K, coupling, and we can calculate percentage of coupling K or percentage of flux of the primary reaching the secondary can be calculated. So first we can know that mutual inductance M equal to K in square root inductance across primary into inductance across secondary. So K equal to M upon square root of inductance across primary into inductance across secondary. Substitute the values. 4 into 10 raised to minus 6 upon square root of 200 into 10 raised to minus 6 into 200 into 10 raised to minus 6. What happened? See here, 4 into 10 raised to minus 6 upon square root of 2 into 10 raised to minus 4 into 10 raised to minus 4 into 2. So here 4 upon 2 into 10 raised to minus 2. So K equal to 2 into 10 raised to minus 2, that is 0.02. But we can calculate. We want to find the percentage of flux of the primary reaching the secondary is 0.02 into 100, that is 2%. Question number 5. Obtain an expression for the self-inductance of solenoid. Consider a long air-cored solenoid of length L, diameter D, and capital N number of turns of wire. Let us assume length of solenoid is much greater than the diameter, so that the magnetic field inside the solenoid may be considered as uniform. Let us consider I be the steady current in the solenoid. The magnetic field with the solenoid is B equal to mu naught Ni. Let small n equal to capital N upon small l is called number of turns per unit length. So capital N upon small l is called number of turns per unit length. So magnetic flux through one turn is phi m is equal to BA, which is equal to mu 0 NIA. Hence, self-inductance of solenoid is capital L equal to capital N phi m upon I. We know phi m is directly proportional to I. So, capital N phi m is equal to Li, where L is self-inductance. So, L equal to NL phi m upon I. NL is equal to NL mu 0 NIA upon I get cancel. So, capital L equal to N square L mu 0 A, where V is area gunile length called volume. So, self-inductance capital L equal to N square mu 0 V, or V equal to pi r square L. So, again self-inductance capital L equal to N square mu 0 L in bracket pi r square. We know R is equal to diameter upon 2, or diameter is equal to twice R. Self-inductance capital L equal to N square mu 0 L in bracket pi d square upon 4. So, L is equal to N square mu 0 L pi d square upon 4. Here, we can write capital L upon small l is equal to N square mu 0 pi d square upon 4. Capital L upon small l is proportional to N square, or capital L upon small l is proportional to d square, diameter square, or capital L equal to mu 0 N square V, which is the expression for self-inductance of in solenoid. Question number 6. A plane of coil of 10 turns is tightly wound round a solenoid of diameter of 2 cm having 400 turns per centimeter. The relative permeability of core is 800. Calculate inductance of solenoid. So, here answer will be given data. Number of turn capital N equal to 10. Mu 0 equal to 4 pi into 10 raised to minus h Henry per meter. Diameter equal to 2 centimeter, which is equal to 2 into 10 raised to minus 2 meter. Radius equal to diameter upon 2. 2 into 10 raised to minus 2 upon 2, that is 10 raised to minus 2 meter. Number of turn per centimeter, small n equal to 400 turn per centimeter, which is equal to 400 divided by 10 raised to minus 2 meter, which is 4 into 10 raised to 4 turn per meter. And permeability of core K equal to 800. We can find out mutual inductance capital M. So, here we know the formula for mutual inductance is capital M equal to K mu 0 pi r square small n capital N. If we substitute the values, so answer we get by using logarithm and anti-logarithm, answer will be mutual inductance is equal to 0.1263 Henry. Another section is long answer type, that is LA type questions. Each question carries 4 marks. So, first question will be find expression for the power expended in pulling a conducting loop of magnetic field. Answer will be when an external agent produces a relative motion between external magnetic field and a conducting loop so that magnetic force resists the motion. Magnetic force requires a force to do work. This work done is transferred to the material of the loop as thermal energy. Because of electrical resistance of the material, let us consider a rectangular frame of wires forming a loop PQRS with length L, with its plane perpendicular to the magnetic field of induction vector B, which is uniform. The frame of loop is pulled or moved with constant speed V out of magnetic field as shown below. Let at any instant x be the distance or length of rectangular frame of loop in the magnetic field. Loop move towards the right side through a distance dx. We know velocity equal to distance upon time, so v equal to dx upon dt, dx equal to v dt. In time dt, area of rectangular loop is dA equal to L multiplied by dx inside the magnetic field. We know as there is change in magnetic flux by the motion of frame, EMF is induced in the coil or rectangular frame. So E equal to d phi m upon dt, which is equal to d vector A dot vector B upon dt. So equal to L multiplied by dx into vector B upon dt, which is equal to L v dt vector B upon dt. So dt get cancel. Therefore E equal to BLV. Due to motion of rectangular frame, the free electrons inside the magnetic field are experienced a Lorentz force. So F equal to E in bracket vector B cross vector V. In wire PS, force move from P to S, so that current I is flow from S to P. Let a circuit containing capital R across which a cell or battery is there. From Ohm's law, we know E equal to IR. Therefore, I equal to E upon R. Substituting the value of E, so I equal to BLV upon R. In a straight current carrying conductor of length L, so force vector F equal to IL vector B sin theta, as theta equal to 90 degree, sin 90 degree equal to 1. Therefore, force F vector equal to I vector L cross vector B, which is equal to ILB using Fleming's left hand rule. Therefore, force act on side PQ and SR, but force not act on side PS and QR, because theta will be 0 degree and so sin 0 degree will be 0. Therefore, force is equal to BLV upon R into LB. So it is B square L square V upon R, because I equal to BLV upon R. We know there is power, which is rate of doing work. So power equal to force multiplied by velocity, which is equal to B square L square V upon R multiplied by V. And therefore, power expending in pulling a conducting loop is B square L square V square upon R. Question number 2. Describe the construction and working of a transformer with neat label diagram. First, we want to see a transformer. A transformer is an electrical device which uses mutual induction to transform electric current or EMF at one into electric current or EMF at another alternating voltage without change of frequency. Construction. Transformer consists of core. Core is a thin rectangular frame. Across one arm of core, primary is considered. Primary of transformer is considered as input of transformer. Across another arm of core, secondary is considered. Secondary of transformer is considered as output of transformer. So first we want to see primary of transformer. Across the one arm of transformer, primary is consist. Across primary, number of thin or thick copper wires are wound on one arm of core. In step-up transformer, large number of thin copper wires are wound over one arm. But in case of step-down transformer, less or small number of thick copper wires are wound over one arm of core across primary of transformer. Across primary of transformer, input voltage is applied. In case of step-up transformer, less input voltage is applied. But in case of step-down transformer, large input voltage is applied. Secondary of transformer. Across the another arm of transformer, secondary is consist. Across secondary, number of thin or thick copper wires are wound on another arm of core. In step-up transformer, less or small number of thick copper wires are wound over another arm. But in case of step-down transformer, large or more number of thin copper wires are wound over another arm of core. Across secondary, output voltage is obtained or formed. In case of step-up transformer, large output voltage is formed near about 10,000 volt to 25,000 volt. In case of step-down transformer, less output voltage is obtained or formed near about 1.5 volt, 1.6 volt, 3 volt, 6 volt, 9 volt, etc. The two figures are drawn: step-up transformer, step-down transformer. So, working can be seen. In working, terminal of primary of transformer, either step-up or step-down, are connected across source of alternating EMF or voltage about 220 to 240 volt. So there is an alternating current through it. Alternating current produces time varying magnetic field in the core of transformer. Thus, magnetic flux is associated with secondary coil. So output voltage is obtained or formed across secondary. In step-up transformer, output voltage is about 10,000 volt to 25,000 volt, but in step-down transformer, output voltage is about 1.5 volt, 1.6 volt, 3 volt, 6 volt and 9 volt. Let capital NP is number of turn across primary. Capital NS is number of turn across secondary. EP is EMF or voltage across primary. ES is EMF or voltage across secondary. IP is current passing through primary. IS is current passing through secondary. For ideal transformer, input power equal to output power. Therefore, IP EP equal to IS ES. But EMF directly proportional to number of turn. So E directly proportional to capital N. So EP directly proportional to NP and ES directly proportional to NS. ES upon EP equal to IP upon IS is equal to NS upon NP for step-up transformer. In step-up transformer, ES is greater than EP. So current IP is greater than IS and number of turn secondary is greater than number of turn across primary. But in step-down transformer, NS is less than NP, ES is less than EP, so current IP is greater than IS. Therefore, ES upon EP equal to NS upon NP, which is equal to IP upon IS. NS upon NP is called Turner ratio. For step-down transformer, Turner ratio NS upon NP is less than 1. But for step-up transformer, Turner ratio NS upon NP is greater than 1. Thank you.